Hello everybody, I'm going to be walking you through the 2017 Calc BC FRQ question number 6. I'm going to be going over how to do each question, what the scores are looking for in each question, so you know how to get a 100% on each part, and I will also be going over the common mistakes so you know what to be careful about. So first off, number 6 will always be a series question on the AP test. It has been and will always be, probably. So you can definitely expect to have series on your AP test, and you can definitely expect number 6 to be a series question. So starting off with question A, it wants us to find the first four non-zero terms of the Maclaurin series. It actually gives us the first four non-zero terms, and it wants us to make sure. And then it also wants us to find the general term. Well, there's something important, and that is that these equations up here, it says that we have derivatives for all orders, -1 to 1, and 0 is between that point. So we can basically assume that there are derivatives for f of 0 all the way up to infinity following this equation. And so we can use that along with the Maclaurin series formula, which we know is just a Taylor series centered around 0, which means we have 0 to infinity summation. This is a Maclaurin series, so it's a Taylor series centered around 0, which means it is going to be the nth derivative of 0 over n factorial times x to the n. And we can use that to find the first four non-zero terms. We're going to expand this. So we start off with n equals 0. This would be our first term. I'm going to highlight that here. And our first term is, we just plug it into the Maclaurin series. So we get the 0th derivative of 0, which is just f of 0, at 0 factorial, which is 1, times x to the 0, would end up equaling us the f of 0 is given to us up here as 0. So we can know that this will be 0 over 1 times 1, which is going to be equal to 0. And it wants us to find the first four non-zero terms. So this actually won't be included in our final four, which means we're going to have to find 4 more after this one, which brings us on to our second term in the series, which will be hopefully our first non-zero term, which will be at n equals 1. So we plug in once again, and we get the now first derivative of f of 0, 1 factorial, x to the 1 is equal to, once again, this first derivative is given to us at the top here as f prime of 0 is equal to 1. And so now that gives us 1 over 1x. So this means we have our first non-zero term, which is x. We move on to our third term. Our third term, which is our second term in the non-zero series, hopefully, but our fourth overall, n is equal to now 2. And we plug in, once again, the second derivative of 0 over 2 factorial x squared. This is where it gets a little bit tricky because we're no longer given direct things, but we actually are given an equation where we plug in, we want to find the second derivative of 0, and we are given that the n plus 1th derivative of 0 is equal to negative n of the derivative of n. And so here, if we want this to equal 2, we know that n plus 1, well, what can we get that to equal to? Well, n would equal 1 in this case, and so we get the second derivative of 0 is equal to negative 1, because n equals 1, times the first derivative of 0, which we know is 1, as given above, so this is equal to, the second derivative of 0 is equal to negative 1, which we can plug back into our Maclaurin series to get negative 1 halves, because 2 factorial is still 2, x squared, which gets us negative x squared over 2, which also gets us our second non-zero term, our third term in the series overall, which moves us on to our fourth non-zero term, hopefully, our fourth term in the series. So we plug in fourth, this will be n equals 3 at this point, and so we now are at the third derivative of 0 at n factorial, which is 3 factorial, which is 3 times 2 times 1, which is 3 factorial, times x cubed, and now we do the same thing with f triple prime of 0, which is equal to f2 plus 1 of 0, which is equal to negative 2 f of 2 of 0, which we just found last problem to be negative 1, so we get f prime of 3 is equal to 2, which we can then plug back into Maclaurin and factor down to get x cubed over 3, which is our third non-zero term. We move on to our fifth and final term, if this is a non-zero, which would be our fourth non-zero term, which is at n equals 4 here, and then we move on. It's the same thing again, the fourth derivative now of 0 over, this time 4 factorial times x to the fourth. We do the same thing again, f3 plus 1 is equal to f fourth derivative of 0, which means we are negative 3 times the second derivative, which we found to be 2 last time, so this would be 2, which is equal to negative 6, so we are left with negative 6 over 4 factorial x to the fourth, which is equal to 1 over 4, negative 1 over 4 x to the fourth, and those are our four terms, which come out to be our first term, which is x. Our second term, which is a negative x squared, negative x squared over 2, plus our third term, x cubed over 3, as we found here, and our last term, which is negative x to the fourth over 4. Now, those are our four non-zero terms, which, as you can see, match up above to these, so we can confirm we probably did it right. And lastly, we got to find the general term for this problem, and we find that by just kind of trial and erroring, but it's kind of, this is an easy one. You can see that this is our n. Our n here is 0, but this is our 0th term, so we cancel that out. And here is our n. That's 1, 2, 3, 4, and this is our n equals 1, n equals 2, and you can see that also is equal on the bottom. So, and it's also alternating, but that's an easy thing, so this is just 0 from 0 to infinity of negative 1, n plus 1. We use the plus 1 there because we want the first term, n equals 1, to be positive, and this would be times x to the n over n, and then that is our general term. Now, for this problem, what they're looking for is it's a three-point question. Each point point can be given by, they want the correct calculated derivatives of using the equation. So the three terms that you found using the equation, which would be this one, or sorry, this one here, and this one here, which I did not highlight. Those would be the derivatives that they are looking for. And they also want you to verify the terms. So getting this right, saying that this is correct to what they gave you, that would get you your second point. And your third point would be by getting the correct general term, which I think is what most people get wrong and is what you should know how to do. It's very hard to do because it's kind of a trial error thing, but if you know how to do it quickly, then that will get you 3 out of 3. Now, moving on to B. Determine whether the Maclaurin series described in part A converges absolutely, converges conditionally, or diverges at x equals 1. So we use what we just found. We use infinity, 0, -1, sorry, that's terrible handwriting, -1, n plus 1, x to the n over n, and we want to find at x equals 1, does it converge or diverge or whatever. So we plug in 1 for x, we get -1 to the n plus 1, 1 to the n over n. I don't know if you noticed, but this can simplify to -1 n plus 1 times 1 over n. Now this is something you should notice, is that 1 over n is actually our is one of our known series which diverges, which means that this could not converge absolutely. So that's out of the equation. Next, we could know if it converges conditionally because it is indeed an alternating series. So we can use alternating series test if a of n goes to 0 and is decreasing as n goes to infinity, then AST is conditionally convergent. Because the limit as n goes to infinity of 1 over n, where 1 over n is equal to an, it's important that you include the limit here. Limit notation is very important and will definitely lose you points, so make sure you have that. And that, as that goes to infinity, will equal 0, and it's positive and decreasing, which means that this series is conditionally convergent due to alternating series test. What they looked for in this question is just does it converge conditionally, which we found it does converge conditionally, and a reason due to alternating series test. This is a 1-point question, and that's the point that they're looking for. The thing that most people get wrong on this question is getting absolute versus conditionally convergent mixed up, and understanding that with that alternating series, we could technically get a conditionally convergent if this limit, and understanding like you need to know the conditions which cause it to be conditionally convergent. That's the main thing that people mess up, and so it's important to understand that. Moving on to C, our second to last, we want to find the first 4 non-zero terms and the general term of the Maclaurin series for the g of x, which g of x is equal to the integral 0 to x of f of t. This one is kind of tricky. We want to just integrate our terms. So what we do is we look at 0 to x of our, so we put in our Maclaurin series once again into our integral, and we expand it out. We expand it out to our first 4 non-zero terms, which we found in part A, and we basically just take the integral of each term, t squared over 2, and t cubed over 3. We use t here just because we're putting it in terms of t because of f of t, and then we just take the integral. So as you can see, once we factor out or expand the summation, we just take the integral of each term like it's a normal integral, and we're left with this, which is just kind of our series, and that's the first part. And then just to find the general term of that, we well, there's a trick to do it actually, and that is to take the antiderivative of the original summation itself. So if you remember, our summation was this, or I guess we could put it in terms of t, and now we can turn it into this here. And that's how you do part C. What they're looking for in this question is that you get the first 2 terms right, and that's a point by itself. You get the second 2 terms right, that is another point by itself. And the last point is the general term, getting this right by itself here. That's how you get 3 out of 3 on this problem. This is a problem that has been seen before. It's not a super common problem, so like the other ones. These other problems on here are very, very common. This is a little bit more of a tricky one, a little bit more of a niche problem, but it's definitely not something to be unaware of. And the thing that most people get wrong on this is the term-by-term integration errors, and just improper integration of this, and an improper finding of the general series, is like the problem we had above. So understanding how to do that is very important. Question D, which is Pn of 1/2 represents the nth degree Taylor polynomial about g for x equals 0, elevated at x 1/2. That's important. G is a function defined in C. Use the following alternative series to show that this is this. So this is actually equal to the remainder 4 of 1/2. So we want to find the remainder for 1/2 is less than 1 over 500, like this. And we can do this with a simple formula, and that is the Lagrange error formula, which shows us that r base n of x is equal to, it's basically a Taylor series but just plus 1. So it's now the nth derivative plus 1, the nth plus 1 factorial, and x minus a to the n plus 1. Plugging in what we were given, we can find that we were trying to be finding our 4 of 1/2 because our x equals 1/2, and this here is 4. So this is then equal to -1 to the 5th over 5 times 4 times 1/2 to the 5th. And this is directly from the equation that we found up here, because this is g of 1 over 2, and we are using g, which we found up here. We're using the general term for g, so we're using this equation, and we're plugging in for n plus 1, which gets us this here, and therefore we are able to find that this is equal to this, which is 1 over 640, I believe, which is less than 1 over 500. So we prove that remainder is smaller. And what they are looking for on this question specifically is just the error bound, just that you get this correctly. And it's pretty simple as long as you know this equation, which is super important, and I will circle in green for you right here. It is the Lagrange error formula if you want to look that up and go more in depth. And a major thing that people get wrong on this problem is not getting the correct n value that we're plugging in here. Remember, we have to do n plus 1 because our bound here is the 4th, and so for the Lagrange error, we want to plug in n plus 1, which is the 5th. So that's something to look out for, and that is your 2017 question 6.